Welcome to our lecture Energy Transition. We'll talk about how to switch from conventional energy supply, just as coal and nuclear, toward renewables. My name is Stefan Krauter. This time we do an online course due to the corona crisis, and my email is stefan.krauter@upb, that means University of Paderborn.de, if you have any questions along the lecture. There will be also a PDF file of the lecture. Also, there will be a video for the exercises and also PDF files for the exercise. You find further information on our web page www.nek.upb.de. We'll give some information about our chair. We belong to the University of Paderborn, to the Faculty for Electrical Engineering, Informatics and Mathematics. We are the chair of Electrical Energy Technology, Sustainable Energy Concepts. Our research areas are sustainable generation and use of energy. For example, we do wind power monitoring and prediction, yield prediction and optimization of photovoltaics, microinverter conversion efficiency and yield comparison. We do energy efficient buildings. We work on decentralized energy systems, and we talk about we teach about virtual energy storage, demand side management, load shifting via remote control of loads. That's really important in order to save the enormous costs for the energy transition, which is in particular the storage costs. Therefore, we also talk about flexibility option, so how we can adapt solar and wind to the consumption. Overview of the lecture is what we'll talk today. This is an overview of the lecture. We'll talk about energy units, the aim, why we do that. So issues are climate change, sectors of energy transition, and tasks to do. The following lecture will deal about conventional energy supply, just as coal, gas, oil, nuclear. We will talk a little bit about thermodynamics, about capacity factor, about the composition of energy system, grid levels, grid composition, and daily and seasonal load curves. Then we'll come to the renewables energies, first to the fluctuating renewable energy, just as solar energy and wind. We start with solar. First we'll talk about solar irradiance. Then we talk about the conversion of solar irradiance, first traditionally, historically, via solar thermal energy conversion. Then we go to the direct conversion of solar energy into electricity, so-called photovoltaics. Talk about the principle and its characteristics. Then we talk about photovoltaic systems. Then we switch to wind power. So we talk about the principle of wind power, its parameters, its converters, its historical and actual development, sizing, including a converter, storage, and transmission system. Then we'll talk about renewable energy, which have a constant power output. First, traditionally, historically, that's hydropower. Then we'll talk about geothermal energy. Then we will talk about biomass. Then we will talk about energy storage, a very important chapter. We talk about the different technologies, so mechanical storage, thermal storage, electrical storage, and so on, the parameters and the costs, including newer technology, just as lithium-ion batteries or the power-to-gas principle. Then we talk about perspective and feasibility of energy transition. So we compare different countries and regions, diesel substitution, conventional versus smart energy, the grid control, balancing power via demand side management, for example, controlled charging of electrical vehicle. We talk about the different simulation tools, first for irradiance, Then for the systems, just as a Homer or PV Syst, or for irradiance, it's metronom. Then we do excursion. This is not sure. This is from last year. We will see how the possibilities are then. First, let's talk about the very basics, the energy units. In every test, I found mistakes by that. So therefore, it's the first we will discuss about. So in general, nowadays we have SI units, not BTUs or kilowatt hour. Theoretically, we should express everything which deals about energy in joule. Kilocalorie was formerly used, but while we are in an electrical engineering institute, we use a lot of kilowatt hours. So sometimes you hear both the joule and the kilowatt hours from us. We won't use kilogram of coal, the crude oil and the natural gas. This is if we don't use these resources anymore, it doesn't make sense to use it as a unit. On the other, additionally, these units are not constant. This depends on the kind of coal, the kind of oil, and the kind of gas. So we would avoid those units. So let's talk about kilowatt hour. One kilowatt hour is 3,600 kilojoule. And here you see this amount and the conversion here from joule into kilowatt hour is 0.000278. Very important and often wrong are the abbreviation for the designations. So we have, for example, kilo. This is with a small k. If you use a big K, this would mean Kelvin. So always use a small k, and this means by a power of 3, 10 by a power of 3, or factor of 1000. If you use mega, use a big M. If you would use a small m, it would mean milli. That would be 10 to the power of -3. So there's a huge difference between that. Giga, the big G, it's 10 by a power of 9. And if you have tera with only one R and a big T, 10 to a power of 12. Peta, 10 to a power of 15. Exa, 10 to a power of 18. We will use these units, for example, if we talk about world's energy consumption. Exa is quite a common unit then. The smaller units, just as milli, micro, and nano, we probably won't use in this lecture, but it's important to know. Just keep in mind and don't mix it up. Here we see the world's energy consumption. We see that a large quantity is fulfilled by traditional energy sources. Renewables don't take a big share in that. That's disappointing, but on the other hand, if you take a look, for example, at mineral oil is often used in vehicles, and a combustion engine is very inefficient. So only about 30% of its internal energy is converted into the mechanical energy. If you substitute that mechanical combustion engine by an electric motor, efficiency is much higher, the vicinity of 90%. If you add a battery, maybe it's 80%, but still by far much higher efficiency and energy use than combustion engine. So later, if we switch towards renewables, that means we will also do an electrification of the energy sector. That would mean we also have much lower need in primary energy consumption. Better even if we avoid the word primary energy consumption, because we better to talk about energy needs. What final energy do we need? How much energy we need as a mechanical energy, how much we need for lightning, and so on. And therefore we'll avoid this expression primary energy consumption. Here we see the relative types. It's the last time we used primary energy consumption, but still it's because it's so widely used. We see the increase of renewables. Unfortunately, don't take a big part. It's about the size or about the share that nuclear energy has. But on the other hand, if you take nuclear energy as an example, there's also a large waste of that energy, because only about 30 to 40% of the nuclear thermal power is converted into electricity. The rest is usually wasted. And this is different. If you have a photovoltaic energy converter, you directly get electricity out of it without a lot of waste. Also, we have to consider the population growth. So we have now in the vicinity of about 7 billion people and the consumption of about 22,000 terawatt hours of electricity. If we switch towards electricity only, so we have to substitute the mobility sector also to electrical, and also the heating sector, which is also more efficient rather than to burn fossil fuels, because you can use heat pumps. If you use it for space heating, office heating and so on, the heat pump has a efficiency which is about 3 times higher than burning fuels. What are the reasons, or what are the aim and motivations for energy transition? So first, it started in Germany. It was the abandonment of nuclear power. So it was a problem that a really secure operation cannot be guaranteed, even in industrialized first world countries, and probably much less in most other countries. There is no commercial insurance for operation, so the liability is transferred to the government, or in other words, to the people. So if something happens, you are not insured, and you have to bury the debt, or maybe the government has enough money to help you. It's also that's also an indirect subsidy, so they don't have to pay that, while every other energy supply has to do that. And also there are a lot of favorable legislation for nuclear operation. It was very fashionable in the 60s and 70s, and therefore the government gave a lot of direct subsidies, but also a lot of indirect subsidies by a favorable legislation. The final waste problems is not solved. In all countries, you have to remember, if you have plutonium like a leftover, you only lose about 50% of its initial radiation after 12,000 years. Proliferation. So there's a lot of talk which country should be allowed to use nuclear energy. Will Iran be allowed, or Brazil was always allowed, but now the government changes. So this is really also a big issue. How you want to make a world power supply if you exclude many countries of that. Also, what people forget, that uranium resources are quite limited. So there are only a couple of countries that deliver uranium, and if the whole world would run on nuclear power, including all sectors, mobilities and so on, the resources would be depleted in the vicinity of 1 generation, 30 to 40 years. Another motivation was the reduction of carbon dioxide and other greenhouse gas, GHG, greenhouse gas emissions. This was not so much related to nuclear power. This was more related to conventional energies, just as lignite and coal and gas burning. The climate change becomes more evident. We have a lot of melting of glaciers, the rise of sea levels, droughts in many countries, and more weather extreme. So we have sometimes very high temperature, sometimes even very low temperatures, stronger and frequent storms, and very inhomogeneous rain. So sometimes we don't have any rain at all, and then we have suddenly a lot of rain. This is not very helpful for agriculture, and therefore it leads to starvation in many countries. Where does the carbon dioxide come from? It comes from burning of fuels just as oil, gas, and coal. And we have only a few relatively small share without CO2 emissions. That's nuclear power, that's hydropower, which was with traditional renewable energy sources. But now it's increasing, as you see here in this graph already. The blue line here, the Here you see that after the year 2000, other renewables are in decrease, and they overtook nuclear power. Here you see the big increase of carbon dioxide in the atmosphere. This is a bit outdated. Now we have more than 415 ppm. So that means parts per million. That means 0.41% of carbon dioxide in the atmosphere. It might sound little, but the greenhouse effect is quite considerable. So it means that the carbon dioxide is totally transparent. It's also not poisonous, because people say it's poison. No, it's not. But it's transparent in the visible part, but non-transparent, opaque in the infrared part, and therefore it leads to a heating up of the planet surface. That effect is sometimes useful. Without the natural greenhouse effect, we would have a temperature which would be 33 degrees colder than we would have today. But now we are exaggerating it by putting additional greenhouse gases in the atmosphere. That's not only carbon dioxide, that's methane, which is about 25 times more climatic active as carbon dioxide. And we have an increase in temperature. Here you see the radiation balance of the Earth. So we have an incoming radiation average of 342 watt per square meter. So that includes day and night and the different region on the Earth. So usually, if you listen to the lectures of solar energy or energy transition or energy technology, we talk about solar energy use, and their standard test conditions are in the vicinity of 1000 watt per square meter. Here we only talk about a third of that, 342 watt per square meters, because due to the change of day and night and so on, and the seasons and the position of the sun and the different seasons. And only a relatively small part, it's about the half, arrives on the surface. The rest is either absorbed by the atmosphere, 67 watts per square meter, or reflected by the clouds aerosol in the atmosphere, about 77 watts per square meter, or reflected by the surface. This plays now an important role because when the glaciers are melting, the reflectivity of the ground surface is decreasing. So we would have now a lower part which is being reflected relatively if you take the whole world. Also, additionally, if you have a lot of fossil fuels, they also emit a lot of ashes, and ash is black, and they also inhibit the reflection on the ground surface. So we have the heating up of the planet, and this leads to thermals. So means hot air is convecting up into the sky. This is about 24 watts per square meter. Evaporation is even more. Sometimes people forget that. So evaporating water is able to transport an enormous amount of energy towards the sky, and there it comes down with rain, and we have also some emission here from the clouds here, and this leads to a cooling of the atmosphere. Some people even say that this effect is really important because the trees which are reduced now to the to fires, but by human activities, this leads to a reduced evaporation of the planet and therefore lead to additional heating. Then we have the surface radiation, which depends on temperature by a power of 4. So we have, if we have high temperature, then the surface radiation is increased. Then we have the back radiation here due to the greenhouse gases. As I told, these greenhouse gases are not totally caused by humans. There are also natural greenhouse gases. Without them, the Earth would be 33 degrees colder. And but now we are increasing this, and so the back radiation will increase. Therefore, the absorption by the surface will increase and lead to additional heating. And then we have here the outgoing long wave radiation, the infrared radiation, as I mentioned. This is influenced by the greenhouse gases. Here you see again just a scheme of the greenhouse effect. So here the radiation exchange is altered due to the low transparencies of the greenhouse gases in the infrared region where the ground surface is emitting thermal radiation. And these are the estimations, the global warming projection. So you see here, even the lowest projection says that we have an increase of 2 degrees. Others say even it will go up by 5 degrees. If I say degrees, it's never Fahrenheit. It's either Kelvin or Celsius, just to mention. This was just a study by MIT. Also, we'll use some further data of them. No, this is by Mr. Ramsdorf from the Potsdam Institute for Climate Effects. And you see here that here the temperature increase was quite considerably, especially during the last 20 or 30 years. We have a considerable increase in temperature. And if you go back in history, you see there is a almost perfect correlation between carbon dioxide and temperature changes. So if you go back here 150,000 times before Industrial Revolution, there are other graphs which even go back further of a 500,000 years before Industrial Revolution. And you see that this correlation, but also quite important to see if you take a look at the scale here. This is in the vicinity of 200 to 300 ppm. As I told you before, nowadays we have in the vicinity of 415 ppm. So that's more than ever happened to be in the history of humankind. Or if you go back 500,000 years, it's really a long time ago, and such levels have never been reached during that period. And you see the correlation here. So if carbon dioxide goes up, also temperature goes up. Here you see some people say, it's a sun effect. Yes, there is a little bouncing of the solar irradiance here, as you see on this yellow line. But this effect on temperature is rather low. So the main effect is really carbon dioxide. It's not only that the temperature it's a bit warmer and so on. It also, these weather effects caused by the climate change are horrible for some people. Not so much in Germany, but many countries suffer by that. This is are the economical damages in $1 billion. What happened during the last 25 years? You see there's a big increase. Not the graph is older. This is more than 65 years. But you see that during the last 25 years, the economical damages caused by flooding, hurricanes, and so on increased considerably. Only here you see the Kope. This was an earthquake which caused considerable damage. But most of the other catastrophes or natural disasters are caused by flooding, hurricanes, and so on. You see these effects of global warming also by MIT. They show here that if we have a temperature increase of 2 degrees, okay, this is already happening at 1 degree, that the crop yields are falling, the glaciers melt, and this will lead on the long term to water shortages. So because the water is not stored anymore in the ice, and many countries, just in Asia, India, there is a lot of ice or water being stored in the Himalayas, and if this doesn't exist anymore, it will be depleted during the year, very soon in the year. And at the end, it will even lead to rising seas. So many countries, just like the Netherlands, Bangladesh, and so on, they are very, or just the oceanic countries, Polynesia and so on, the sea rises only by half a meter, they will have severe problems. Reefs damaged, we perceived that also Great Barrier Reef in Australia is called reef bleaching. This is not only due to temperature, but also to the accumulation of carbon dioxide in the seas, which makes the seas more sour and more aggressive against the coral reefs. We have species extinction. Can observe this. Don't know how many species are extinct every day, but it's really a lot. And As I mentioned already, we have more severe storms, droughts, fires, heat waves, and so on. And if we go beyond 2 degrees, there could even a very abrupt climate change. If you know control technology, that also happens if you are reaching a certain amplitude, then there could be some snap points which cause severe damage or extreme amplitudes in the end. Let's talk about energy consumption and possible resources. What you see here is a representation of the world's energy consumption during 1 year, this small red cube. If you take our present resources here in comparison, you see here that the biggest cube is the coal resources. So if you would feed the whole world with coal, it would last for 100 years or 200 years. So that would be sufficient. Problem is the carbon dioxide emissions. With oil, it's already a bit less. Natural gas, it's quite easy to see here. It would only last perhaps 30, 40 years if you would supply the world with gas only. Also, uranium, as I mentioned already, is not a solution for all the time. It would, if we would want to avoid carbon dioxide, it would the whole world power by nuclear power plants. These uranium resources would be depleted within 1 generation only. But we have other resources. This is solar energy. It's the amount of solar energy what comes on Earth within 1 year only. The other resources, what I've been mentioning, have to last for all time. So coal, for example, took 150 million years to build, and we basically burn it within 150 years. And so there's no chance that it gets recovered. While the sun here, what comes in, is recovered every year. So we can deplete the sun every year. And it's much more than all known resources of all other energy resources. And about 14,000 times more than the actual world's energy consumption. If we would go on a conservative estimations for the area necessary, if you convert some part of this irradiance, as I told you, we don't need a lot, 14,000 times more than the world's energy consumption, even considering primary energy, which you won't use probably because we have more efficient consumption patterns. And if you further conservative estimate that you have a conversion efficiency of 10% only, so modern PV has a conversion efficiency of 20%, but we take 10% here, and that would be the area you need to supply the whole world with solar power. So this is a Sahara Desert, what you see here. Nobody lives there, or very, very few people live there. And you see the pink square. For the Europe, it would be the blue square. And for Germany, which has about the same energy consumption as Brazil, it would be almost invisible. It would be the gray square. Possibly we won't concentrate all the solar power plants on one spot only. We would distribute in. That helps also if we interconnect the different power plants on the planet via cable. We are able to supply solar power during 24 hours. For example, if sun is going down in Lisbon, it goes already up in the eastern part of Russia, for example, Vladivostok. So if we would interconnect east and west, we would have daily equilibration of the different irradiance level. If you do a north-south interconnection of different power plants on the southern and the northern hemisphere, we would level out the seasonal changes. Here are some examples. These are 6 different spots in original size, and the power required, the nominal power of the power plants would be about 18 terawatts. So presently this would require, this is here mentioned 20 billion euros. Nowadays I would even say it's only 18 not 20 billion, or 20,000 billion euros. Or if you do an update from last year, prices went down. So this is about 18 billion euros, including grid interconnection. Here you see the cost development of renewable energy. This is a graph from 10 years ago. So expectations for these years have been 3 to 4 cents for wind power. This has been fulfilled. For solar power, photovoltaics, people thought it will be in the vicinity of 20 euro cents. That's not true. We went down now even to 2 cents per kilowatt hour. In Germany, we even reached 6 cents. It's written here, but it's actually 4 to 5 cents. So that's a bit outdated than this graph. So the reality was better than the expectation. For geothermal, it's about in the same level, 3 cents per kilowatt hour. Solar thermal, also about biomass also. This is an outlook, interestingly, by the company Shell. As you know, Shell is living from selling oil. And even they take a look at the expectation what they have after the year 2020. They expect that they reach the so-called mid-depletion point. So that means that most of the resources on oil and so on have been depleted. Nowadays it's a bit prolonged due to the fracking. So you lengthen this by another 10 years or so. But sometimes in this next decade we will reach the mid-depletion point, and then even Shell expect that the business with mineral oil is going down, the costs will be high, and most of the world will be supplied by renewables, just as geothermal, solar, biomass, and wind power. Okay, Shell expects that nuclear will still survive and be expanding, as it, but other people won't think. So as we see here that the share of renewables and capacity additions surpassed the investments in conventional supplies. So most of the new power plants are renewables now. This is a scenario for the German energy supply. So you see here will be all substituted by renewables, plus there will be some increase in consumption due to the switch from combustion motors to electrical motors for mobility. Quite interestingly is to see the dependency on imported fossil fuels. Most fossil fuels don't exist in industrialized countries, so we have to import them from somewhere, from Venezuela, from the Middle East, and so on. And due to this dependency, there is a quite schizophrenic approach towards these countries. So, for example, Saudi Arabia is not democratic at all. They can do whatever they want, but because they have oil, they are treated quite good by the West, while Cuba it's also not democratic, but they get sanctioned. Also, consider the wars for oil. If you just consider Iraq, for example, which was proven that there were no weapons of mass destruction and so on. It had other reasons why this war has been fought. And the basic reason is the war for oil. So even the US administration is admitting that. And the costs spent for that have been until 2013 $1,456 billion US. So this is really cost what has to be added to the cost of fuels, and which is paid by the taxpayer, which you don't see on the gasoline price actually. You see here the sectors which are substituted by renewable energies. So we have here the generation, but also we have to adapt the infrastructure and operations. So we have to extend the power grids, as I mentioned. If you really think globally, make an intercontinental connection. This is actually done by the Chinese company, Chinese State Grid, which wants to build a power line from China to Germany and use such effects. What we also have to do, a reinforcement of existing line, enhanced equipment development, energy storage is a big issue, smart meters and so on. Transforming the energy sector. So we have to accelerate renewable energy capacity, in addition to generate adequate power with low carbon technologies. So First, we have to identify and map renewable energy resources and develop a portfolio of financeable projects on the medium to long term. Construct no new power plants and plan and implement an end-of-life phase-out of coal capacities. And we have to update grid planning to accommodate rising shares of variable renewables such as solar and wind power. We have to develop a flexible system. So that's also a bit of a problem. Some people say, okay, we leave the old nuclear power plants and they work in conjunction with renewables, with variable renewables. There's a bit of problem at nuclear power plants. They are somehow flexible, but only to a minimum power of about 30% of their maximum power. Below that, they are not flexible at all. They always have to deliver 40% of their maximum power. Lignite power plants, they are also hardly flexible because you have to plan about 8 hours in advance to do the management. And if you know that wind and solar power, they can change within minutes. So you should have really a backup power source which is able to cope with that. But you can do this is called smart grid with controlled charging of electrical vehicles. So if there's a lot of power in the grid, you charge quicker, and if there's not so much power in the grid, you charge at a lower rate. As an upgrade grid code. So this is the codes which are made usually a long time ago, and they get updated now, so they are more suitable for the digestion of renewable energies. To deploy mini grids to improve the resilience and expand energy access with renewable energy sources. Deploy supergrids, that's what I mentioned when we talked about this 18 terawatt. Deploy a cost-effective tariff structure by probably readjusting the balance between volumetric charges, so US dollar or euro per kilowatt hour, fixed charges, so how much you pay just to have a possibility for an electricity consumption, and demand charges. So this is already happening in industry, so you don't pay by kilowatt hour, but if you have for a very short time a very high demand, this should be considered also in the charges. And we have to incentivize energy consumers to pay to become so-called prosumers. So they interactively play a role. We have to also to support regularity and pricing policies, including rights to generate and sell electricity. There's a bit of a problem. So the so-called balconate power plant. This is still a bit gray area, and if you want to sell your electricity, it's almost impossible to do that as a private prosumer. Tariff regulation and grid arrival policies. So this is called Support Distributed Energy Resource Development, DER. And that's the last thing is that it's enable aggregators to foster the use of DER. So if you're not able to do it as a single prosumer, you can aggregate a lot of consumers or prosumers, and they are more able to deal with the requirements to play a role in the transmission grid and so on, the distribution grid. So what we see here is the final energy consumption for transport. So as I mentioned, there will be an electrification issue, and along with that, we will have also increase in efficiencies. So first, we will emit less carbon dioxide to the substitution by electricity, which should be powered in the future by renewables, plus a significant reduction of energy consumption to the substitution of inefficient combustion engines. Also, what we can do additionally is to reduce transport volume and congestion. So we adopt advanced digital communication technologies to improve transport planning and services. promote mobility service, so autonomous driving, vehicle sharing, and so on. This also helps a lot to reduce traffic. For example, if you got some statistics from Munich, the 60% of the Munich traffic of the inner part of Munich is searching parking spaces. Accelerate the shift from passenger cars to public transport. Deploy low emission city trucks and so on, and accelerate the shift to electric mobility. So that means we have to set minimum standards for electrical vehicle emissions. We have to give electrical vehicles priority in city access. Maybe we can also think about speed limits. Some speed limits are towards noise reduction only, and if you have a silent vehicle, maybe they can have some preferences. Incentivize the development of a charging infrastructure. Okay, that everyone knows. Strengthen the links between the power and the transport sectors with integrating planning and policy designs. So this vehicle to grid services. What I mentioned before, you don't have to charge at a constant rate. So instead of being a problem for the grid, it could really help to stabilize the grid. Introduce specific mandates for advanced biofuels accompanied by direct financial incentive and financial de-risking measures. So this means that we prioritize biofuels in road freight, aviation, and shipping, and adopt supporting policies to scale up sustainable production of first and second generation biofuels, eliminate fossil fuel subsidies, and implement carbon and energy taxes. This is already happening. Now, next year, we already have this implemented. This increases the competitiveness. And now we come to the industry part. So we see here that also a large part is being substituted by renewables. There's also some saving due to the increased efficiency, not as much as for the transportation sector, but considerably. Then we come to the building sector, also a large part being substituted by renewables and electrification. There's also an effect by reduction of energy, but here in this graph you don't see a lot of that. As I mentioned, if you would use heat pumps instead of heating, this effect can be quite considerable. This was the first lecture. So next lecture we will talk about the conventional energy supply. So we'll talk about coal, gas, and nuclear, about thermodynamics, so-called capacity factor. So it's how many full load hours a power plant can deliver power or is allowed to deliver power during a year. And the composition of energy systems, so the grid levels, so mid voltage, high voltage, and so on, grid composition, and daily and seasonal load curves. Thank you very much for listening.